Hello. Good morning. Welcome to the Warren Lecture Series. We are honored to have Professor Nigel Wilson from MIT for today's Warren Lecture Series. Professor Wilson is working at the Civil and Environmental Engineering at MIT, and his research and teaching areas focus on urban public transportation, including topics related to operation, analysis, planning, and management of transit systems. Professor Wilson directs a major long-term collaborative research program with urban public transport agencies, including Transport for London, MTR Hong Kong, Chicago Transit Authority, and the Massachusetts Bay Transportation Authority. He has been a visiting faculty member at the Stanford University, University College London, Napier University, Delft University of Technology, and the University of Minnesota. Professor Wilson received the bachelor's degree in civil engineering from Imperial College London and the master's and doctoral degree in civil engineering and transportation system, respectively, from the MIT. Please welcome Professor Wilson, and without further delay, let's enjoy the presentation. Thank you.
Thank you very much, Alireza, and thank you to everyone here for being here. As Alireza said, I was at the University of Minnesota here 8 years ago on sabbatical leave for about 6 months. Spent half time working with John Levin and his group at Metro Transit, and the other half at the university working with Max and many of the faculty associated with CTS and the department. So it's a great pleasure to be back here. I actually gave a Warren lecture as part of that 8 years ago. I didn't go back and try and find that lecture to see if what I'm saying is redundant, but I think much of it has been developed since then. Anyway, it's a pleasure to be here. I am not too unhappy that the snow missed the Twin Cities last night. I'm sure John and the Metro Transit people aren't too unhappy by that as well. But at least the cold weather here was reminiscent of winters in Minnesota. So what I'm going to talk about today is the role that automated data systems are playing and will play in the future in improving the performance of public transport systems. So it's a fairly broad topic. What I want to do is sort of set up the expectations, things we're all familiar with about what service providers typically do in the private sector, and sort of relate that to public transport. Define automated data collection systems, the systems I'm planning on building on, extracting data from. Present a framework in general terms about how we can think about these problems, and then give 3 examples of work we've done at MIT in connection with the research program in London, Hong Kong, principally those two ones, which are interesting building blocks towards what eventually might be the impact of these tools to use ADS data. So the first one is OD matrix estimation, the second one is inferring train loads, and the third is measuring service reliability, all of which I think are interesting and important in and of themselves, but are potentially very important in terms of how they contribute towards more far-reaching impacts on improving system performance. And then wrap up by talking about future prospects. Please interrupt as we're going along in terms of issues of substance as well as issues of clarification. Don't worry about interrupting. I should be able to retain my flow. Okay, in terms of the general context, again, this is something we're all familiar with. We all deal with Amazon or similar service organizations that seem to know an incredible amount about us and prompt us every which way about what we want to order next after the current transaction is completed. And this is very much the milieu in which we all live. And in some ways, there's a contrast between what public transport agencies have traditionally done and what these new service organizations are tending to do. And so customers have expectations about which are formed by their interactions with these pretty advanced service providers, and may be disappointed if public transport doesn't respond in some way to raise its game. I think obviously we're all familiar with the IT and communication improvements that have occurred and will continue to occur in terms of the pace in the future, I think it's clear that while there are captive riders, there are many more people who potentially might be persuaded to use public transport systems if the experience they receive is consistent with the good aspects of the service they receive from other service providers. So I think it's important there that we're more and more in a trying to attract choice rider situation. And so these are some of the challenges I think that exist. This one, which I've just mentioned, if we look into both the immediate and the longer term future, you've got autonomous vehicles in the midterm future. Who knows exactly when? I'd defer to Max on that. But certainly, in many of our lifetimes, autonomous vehicles will be with us. How will that affect public transport, and how should public transport be anticipating that new world? And on a more immediate front, you have Uber, Lyft type services, which for the student generation now are becoming the default form of mobility as opposed to public transport. So when I'm in a lift or elevator at MIT with students, I never really hear them talking about using the T. They're always talking about, well, I'll call Uber and we'll do this. It's just a fundamentally different mindset than the one I grew up with, and that's part of the reality that public transport agencies have to deal with. So this is some of the context. So starting out in the mainstream of what I want to talk about, what are these automated data collection systems? Well, they're the AFC systems, the go-to card, which I have in my pocket and still works after 8 years, which are transaction-based automated fare collection systems, which I put them first because I think in many ways these are the most important. I think these are the most important because they're transaction-based, which enable you to understand what the individual has done, what I as an individual, how I have used the system in terms of where you've boarded, perhaps where you've alighted in some systems, not necessarily. Traditionally, in some systems, these provide exit information as well as entry information. In some cases, you work on an honor system, and so there isn't any barrier as in the Metro Transit light rail system. So you don't have as much of this information readily available, but in some systems you have both entry and exit information, including both London and Hong Kong. This is traditionally not available yet in real time. I think it won't be too long before this information will be available in real time for the control center, for decision makers in the network, and that will be an important change. AVL systems, bus systems based on global positioning systems, train tracking systems based on track circuit occupancy, provide real-time information on where the vehicles are, which are critical for managing the system in real time. And APC systems, again, bus systems based on sensors and doors, and many new train systems have loadway technology, so you have an estimate of the weight of the train, to control air conditioning and braking systems, and that enables you to make an estimate of the passenger load on the train at a particular point in time. This is, again, traditionally not available yet in real time, but it's not unreasonable to expect that in the future these things will be available in real time, and we'll be able to help we'll be able to take advantage of them in controlling the system. So these are the fundamental systems I'm talking about. The changes, the impacts they're having on the public transport system are like the impacts they've had on many other organizations. So the cost structures change fundamentally, much lower marginal costs once you've invested in the system. The cost of gathering additional data is very small compared with manual systems where the system itself doesn't cost very much, but every time you send a checker out into the field, it's costing you a fair amount. So the marginal cost going down has a fundamental impact on how large a sample size you can obtain. You can obtain much larger sample sizes because of the low marginal cost of gathering data. There are limitations, obviously, in terms of the data you get. The automated systems give you what I think of as hard data, numerical data, whereas the manual systems give you hard data, but also soft data, attitudes, perceptions, preferences, those sorts of things which you can't, at the moment, maybe in the future, you can't get out of these automated systems. However, the manual systems are unreliable, and automated systems are also unreliable in the sense they have errors and biases, but you can begin to quantify those and correct for them, so you get pretty good data that you can use out of these systems. Because of all of these characteristics, the automated systems tend to be ubiquitous, whereas the manual systems are very limited spatially and temporally, and you have to be very careful how you use them. And I think the other big impact is that increasingly these are available in real time or quasi-real time, whereas these are not available in real time. So there are very fundamental differences, I would argue, between the new automated data sources and manual. So the potential of this is that you can think of this automated ADS data warehouse, if you like, which can support a whole range of models and software, which in turn support many agency decisions, all built around this data warehouse. This can give you insight into both normal operations, the everyday operations, but also operations which occur sort of once a year. So first night or July 4th celebrations or big sporting events that don't occur once a year but occur periodically. You can really understand those, the way the system's functioning in those non-everyday events, and optimize the performance for those non-everyday events, which is, I think, very important in terms of the choice writer, because these are often the way the choice writer experiences the system for going to a sporting event, going to a celebration of some sort. And if you can improve that experience, you have a much better chance of really making that a more regular user, that individual more regular user of public transport. So I think it's very important. And because of the cost structure, the automated data collection systems give you the ability to do this. The other point I want to make here is in terms of giving you large, long time series disaggregate panel data to really understand how individuals are perceiving the system and reacting to the system. So as you change fares, as you change reliability, as you change the network structure, how are people reacting to that? This panel data set that you can get from individuals gives you, for the first time, the ability to really understand how people are changing their behavior in response to changes you're making in the system. So I think all of these are tremendous sources of potential. The reality, however, is quite different. We're not there yet, and there are challenges. So many of these systems that I talked about are implemented independently, and they're not primarily designed for data collection. They're designed for some other very important activity within the agency, such as emergency notification and stop announcements, fare collection and revenue protection for AFC. Data collection is a spin-off benefit of these things. So these systems aren't designed usually for easy access to the data and for the right data to be collected. So there are many problems to overcome. It's not easy to integrate the data. In some cases, not easy to get hold of the data in the way that you can use it. And it requires new sources, new resources, and expertise within the agency, which you're going to have to compete with the private sector on, and that can be quite difficult. So there are lots of challenges, but the opportunities are also great, and I think the potential impacts are tremendous. So obviously, we can use these systems for monitoring system status in real time, for measuring reliability. We've all known, those of us who've been interested in public transport, all the surveys have always said reliability is the most important attribute. But we haven't really been able to measure reliability until we have these automated data collection systems. And if we can't measure it, it's very hard to improve it. So I think that second thing is quite important. And understanding customer behavior, as I mentioned, through this long time series panel data analysis is, I think, another very important opportunity. The second general area of opportunity is data and computing. And I think this comes down to, in the control center, having these simulation-based performance models to help predict what will happen in the network, in the system, if we do certain interventions in real time. And I think we're not there yet, but that's a real opportunity that I think we're getting close to. communications, real-time information on the demand side, which we're all familiar with through NextBus and things like that, and operations management. How do we really control the delivery of the service through the information coming back from the systems? And fundamentally, these ADS systems give us the opportunity to provide a more systematic approach for the planning, operations, and real-time control of the systems. And these are, I think, very, very important potential benefits. So I want to talk next briefly about what the functions within the agency that can be affected by the ADS now and in the future. I'm distinguishing here between the offline functions, which don't occur in real time but are very important, and the two principal ones I would say are service and operations planning, so network and route design, frequency setting and timetable development, and vehicle and crew scheduling. Many of these are already being affected by various of these ADS systems, but I think the potential impact in the future is much greater than we've seen to date. And the second general area of offline functions is performance measurement. These systems give us the opportunity of really assessing how well we're doing in a very systematic way continuously over time. This is particularly important in many parts of the world, not so much the US, although there are examples of this. You have a standard organizational regime where a public authority monitors the service and enforces contracts, and the services are delivered by private providers under contractual regimes. And so unless you have a very effective way of measuring performance, it's very hard to enforce performance penalties or financial incentives. And the ADS is a fundamental unit of that. And then secondly here, under performance measurement, measuring the customer experience I think is much easier, although albeit with hard data, to do with these automated data collection systems than we could traditionally with manual systems. So those are the main offline functions. The real-time functions are on the supply side, the service and operations management and control functions. So dealing with when something goes wrong in the system of a minor or major nature, how do you adjust the operations plan to deal with that? How do you manage the delivery of service? And when you have unexpected surges in demand or unexpected changes in demand, how do you alter the operations plan in response to that? So this is the supply side response to the supply side aspect of real-time functions. And of course, the customer information is providing dynamic information on how the system is. So you cannot just make a decision about where and when to access the system, but how to change your strategy as you navigate the system. So this then is the framework that we're using to think about this. At the core of the system, you have this system monitoring, analysis, and prediction function. We can think of this as a control center, which is being fed by the automated data sources, providing data on where the vehicles are, how loaded the vehicles are, what the state of the system is, and on the demand side, information on how people are using the system. The offline functions that this control center supports are performance measurement as one of the major offline functions, and then the feedback loop through service and operations planning to modify the operations plan, to modify the network over time in response to what we're observing in terms of the performance. So this is the supply side loop in terms of the offline function, and this is the demand side loop in terms of the offline function. The real-time functions are the service management one, which is modifying the supply, the control center being fed by ADS, using its functions to decide how you want to modify the delivery of service in real time here, and the customer information, providing information on the current state of the system to customers so they can make better decisions about how to use the system. So this is the real-time demand side loop, the real-time supply side loop, the real-time demand side loop. So that's the framework that I think is already driving what we're doing in terms of development of new systems. So with that as the framework, I'm going to now go into 3 building blocks that we've developed, that we've been working on at MIT. And MIT isn't the only group that's working on these sorts of things, but we've done some, the work I'll present is the work that we've done in these areas. The first is origin-destination matrix estimation, understanding how the system is being used by customers. If we don't understand how it's being used, it's very hard to improve the system. The second one is inferring train loads, and I can envision a point where we can be given information on our smartphone or at a stop saying not only when the next vehicle will be there, but will we be able to get on the vehicle? It's very frustrating. I'm sure we've all been in this situation where, yes, the vehicle arrives pretty much on time, according to our real-time information, but it's full, and the vehicle doesn't even stop there because it's so full. I had that happen to me in Boston 2 days ago. It's frustrating. So I think the issue of inferring in real-time train loads is a very interesting, challenging research question that can really affect the perception of these systems. And then the third one is measuring service reliability. So I'm going to talk a little bit about each one of these. So origin-destination matrix estimation. So what we're trying to do here is estimate the passenger origin-destination matrix at the network level, the public transport network level, using AFC data, the transactional taps through your through your smartphone or smart card, and the AVL data. And so what we're trying to do is here understand multimodal within the public transport context, passenger flows on the network, and what the underlying demand is. The AFC automated fare collection system characteristics could be open, which implies entry fare control only. So you tap when you get on a vehicle or get to a station, but you don't tap when you get off the vehicle or at the exit station, or closed systems which have both entry and exit fare control. And the examples I'll give are mixed systems, the hybrid systems, which London, for instance, on buses, you tap when you get on a bus, but not when you get off. On the underground, you tap when you get on, and you tap when you get off. And what we want to do is understand the full journeys, not the individual links, but the full journeys. I started my journey here on the public transport network. I ended my journey here on the public transport network, and it includes buses and trains as you go along. I've got references on all of the work I'm describing here that if any of you are interested in any of this, please speak to me after the seminar. I can get you electronic copies of these various things. Okay, so the basic idea of how we do this in open systems, where you don't know where the individual got off a particular vehicle, is through trip chaining. So we basically sort all of the transactions on the smart cards by card number. Every transaction has a card ID on it, transaction type, and transaction time. So for a particular card, we do a chronological sorting on all the transactions on that card that day. And we get a series of transactions like this. So we have transaction at A. This is assuming it's an open system. We just have tap on entry. First is at A, second is at B, third is at C, and the fourth is at D. And what we're trying to do is understand where this individual who tapped on at A actually alighted. So the simple idea here, which all of these systems use, is that probably you alighted on the route you boarded at the stop closest to your next point of access to the system. Okay, so what you're doing here is saying, okay, TS1 goes from A, which is a known point, to the point on the route you tapped on, which is closest to B, which is your next recorded tap location. It may be 8 hours later, but probably that you got off that route very close to the next point of boarding. Won't always hold, but very many cases it will hold. It's a reasonable general rule. So again, the argument here is the destination of many trip segments, TS is a trip segment, is close to the origin of the following trip segment. Won't always hold, but in many cases it will. So for destination inference, what we're doing here is this is a tap on route 1. This is the next tap on route 2. And we're saying we locate the stop or station on route 1, which is closest to the next point of boarding on route 2. And so that's defined as the destination of that trip segment. And we go through this. Similarly, on route 2, the tap here is succeeded by the tap on route 5, which may be 8 hours later. And so we look for the stop or station on route 2, which is closest to the next boarding location on route 5. And we infer this to be the destination of that trip segment. Now, depending on the times for these interchanges, there may be an activity there, which implies it's the end of the previous journey, or it may be just an interchange activity, because it wasn't long enough to do anything except perhaps grab a cup of coffee, which you could do anywhere. It's not the purpose of your trip. So in this case, these two trip segments would be linked and say the real origin of the trip is at this point here, the real destination of the trip is at this point here, and because of the network structure, you had to have two trip segments to get there. This might be an 8-hour gap between the inferred alighting time on route 2 and the recorded boarding time on route 5. And we say, well, there was clearly an activity going on there. That wasn't an interchange. It's far too long for that. Maybe it was a workday at that location. And so this would be the beginning of a separate journey which started at this point and ended at this point. So this is the fundamental way the inference process works. And this is just showing, again, because of the times between inferred alightings and recorded boardings, that these two trip segments would be linked as one journey. There's a long time gap here between the inferred alighting and the next recorded boarding. And so this would be a separate journey, which go into the origin-destination matrix. So the key assumptions for this whole process to hold water are, first of all, there are no intermediate private transportation mode trip segments. So I don't get off a train, take a taxi, which is not part of my system, and then get on a bus. Will I ever do that? I might do it on some occasion, but it's not a typical behavior. And we're not understanding, in this case, the individual behavior. We're trying to get an aggregate picture about how the system is being used. So individual errors aren't of great concern to us here. Secondly, passengers will not walk a long distance. What does that mean? Maybe it's a kilometer or a couple of kilometers. It depends. But at some point, if you have a long enough gap between the inferred alighting location and the next recorded boarding location, you say something else is going on here. We don't want to build this in as a single trip. So we just throw that out, and that's part of the uninferred journeys. And the sort of wraparound, the last trip of the day ends at the origin of the first trip of the day, or the first trip of the next day ends at the location of the last trip of the previous day. That's so you get that, you record that last journey. Will all of these hold in every case? Absolutely not. Will they generally be holding? Yes, they will generally be holding. And we'll have a good aggregate picture of travel if we use these assumptions. So this is from London, just to give you an example of a journey. You can't see the individual dots here, but someone boarded a card associated with someone, boarded East Croydon National Rail Station at 7:46, did an out-of-station transfer to Central Line at Shepherd's Bush at 8:30, exited the Underground at White City at 8:35, boarded a bus at 8:36, and alighted the bus at Hammersmith Hospital at 8:42. So this is clearly a journey. All of the intermediate things were interchanges rather than activities. Journey 2 starts at 6:17, so there's a long gap here. This is a workday at or in the vicinity of Hammersmith Hospital. Boarding a bus, alighting a bus, boarding a bus, alighting a bus, entering the Underground, out-of-station interchange, and winding up at this location here at 16:56. This is the second journey. So we can understand fairly complex journeys and piece them together as journeys as opposed to individual trip segments. And it's really important to understand the way the system is functioning to understand what these full journeys are. rather than individual trip segments. So the trip chaining method for OD, origin destination inference, is we infer the start and end of each trip segment for individual AFC cards, for individual media transactions. We link the trip segments into complete one-way journeys, just as I illustrated previously. We integrate the individual journeys. We add together the individual journeys that we've pulled from the AFC data into a seed origin destination matrix, which describes all movements in the network. And then we expand. Since we're not inferring destinations for all journeys successfully, we have to expand to represent the full travel. And the expansion is based on any available control totals. So for instance, we might have control totals which are station entries and or exits for rail, passenger entries or exits by stop, trip, or period for bus through the fare box on the bus. These gives us control totals in which we can expand the seed matrix. Okay, let me give you an illustration of the London example here. This method we began to develop in Chicago in work for CTA. We sort of refined it in London, and what I'm going to present here is the London model. We now brought it back to use in the MBTA and in Chicago again, and we're developing sort of a general method for doing this that we use anywhere. So the size of the problem in London, Oyster fare transactions per day, about 12 million, 6 million on rail where you're tapping in and tapping out, so it's about 3 million customers a day, and on bus 6 million entry only. So you've got twice as many bus customers as rail customers. But it's a big problem. It's a large database. For bus, the origin inference rate is about 96%, so we're getting almost all the bus entries are being recorded. You get some failed equipment, so that's where the 4% comes in. The destination inference rate for bus, where we don't know anything without the inference process, is 77%. So we're doing pretty well. Now note, I say the inference rate. I'm not saying the successful inference rate. Some of these will be wrong, but we're making some sort of guess, in a way, at where they're getting off. So for the full London public transport network, we have 76% of all fare transactions included in the seed matrix. So this isn't a small seed matrix. This is a seed matrix that represents 75%, 3/4 of all of the journeys in the network. So the expansion problem isn't as significant as you're used to thinking about if you have it starting out with a small manual survey, for instance, where you've got very large expansion problems. In terms of this is computationally feasible. It takes about 30 minutes to run this whole thing, including all of these steps on a day's worth of data in London on sort of a non-powerful, just a standard PC. So that's pretty good. So London has what they call industrialized this. It's gone from the research shop at MIT to testing to acceptance, and they've reprogrammed this within TfL. So this is what they do for monitoring usage of the system. So it's no longer a research tool. It's really a production tool now. And we hope and believe that the MBTA in Boston and CTA will be doing similar things very, very soon as we do this. This is, can we switch the lights off for a couple of minutes? Is that here? Because you have to have this in the darkness. Okay, so this is as a day in the life of London public transport users. The time of day is here. So this is now 7 a.m. Green is movements on the network from the origin to the destination. Red are people who are at home. Sorry, blue are people who are at home. And red are people who are involved in activities away from home. Okay, so those are three basic colors. So this is now 10 o'clock, so it's after the end of the AM peak. So there's lots of red in the network. People are at work. They're doing other things as a result of using the network. As you head towards the PM, you'll begin to see more and more green radiating out from central London, where most of the activity is. So it's now 1 o'clock, 2 o'clock. There's not a lot of activity on the network, very little green. As you're going towards, this is now 3 o'clock, you'll see more and more green, and you'll see the rays emanating out from central London to the outer areas of London where many people are living. And so that you see this strong radial emanating pattern from central London out into residential areas. It's now 6 o'clock, sort of the end, and you're now beginning to see more and more blue where people are already at home. As it's now 7 o'clock, you still get a fair amount of activity in central London. A lot of people engaged in fun activities in central London. But more and more activity is at home, indicated by the blue, and less red and less green as there's less travel on the network. So we're now just about midnight. Soho is still very active in West London, but there's more and more blue and things are quieting down. So this is a very evocative image of the way London functions in terms of the public transport system functions and supports life in London. This had a lot of impact on sort of decision makers and elected officials when we first did this, which was now 3 or 4 years ago in London. We're doing the same sort of thing for Boston and Chicago, and it really gives you a visceral sense about the way the public transport system is being used, so as opposed to the individual level, a big overall picture. So that's all I want to say on the OD matrix estimation process, which is the first one. The second one is inferring train loads. This is work we started out in London, and we have continued in Hong Kong with MTR. And we've now brought it to the point of, it's not industrialized fully in MTR or London, but we think it's well on the way to that. So the idea here is to develop a method to, quote, assign passengers to trains using the AFC and automatic train regulation, ATR, data. And we can support through this understanding the way lines and segments of lines are being used, service quality metrics from the customer's point of view, the crowding on trains and in stations, the number of passengers left behind, and more detailed journey time metrics. This is work that was done at the master's level by a student. She's now just finishing her PhD, which goes well beyond what I'm presenting here on the same general area. So the essence of this, as in the previous case, is very simple. So what this shows is a time-space diagram, and we're dealing with a closed system, as we have a fare collection system, as we have in London and Hong Kong. So someone taps in at this entry gate at this time, and taps out at this exit gate, fare gate, at that time. And the question is, what train were they on on this line? And I'm presenting the simple no transfer case. In the general case, you have route choice and transfer, and multiple trains on each of the links of the trip. So you could have taken train 1, train 2, or train 3 in this case. It would have affected how long you spent it accessing from the fare gate to the platform. This is a very short access time. And how long you spent egressing from the platform to the fare gate. And so the method here is to choose using maximum likelihood estimation methods to say, well, what's the most likely train that you are on? Again, you won't be right in every case, but it'll give you a pretty good forecast about the number of people in aggregate who are on a particular train, which is what we're interested in doing. So we're saying, what's the probability of observing this access time and this egress time relative to the other trains that were in the feasible set? This is a particular example in the off-peak from MTR in Hong Kong, which shows the number of feasible train itineraries. How many trains were in this set between your tap-in time at station A and your tap-out time at station B? And what this is showing is, in this particular case, you generally had no more than 2 itineraries, and you had a fair number with only 1 itinerary. So for those of you who are interested in the modeling aspects of this, you can use your 1 itinerary set, where you know what train they were on, to estimate the access distribution and the egress time distribution, okay? And then you can apply that to determine the maximum likelihood choices for the multiple itinerary case. Okay? So we have a simulation here which shows this. We have a train traveling down this line. These are each stations, and at every station you have passengers boarding and passengers alighting. And this is the particular visualization that I'm going to use here to illustrate this. So you have this is one line. The squares are stations. The rectangles are trains serving the stations. This gives the time here, just about 1 p.m. These are an actual line in the MTR network, the beginning of the line. And you'll see passengers beginning to come in at 1 o'clock, accumulate on station platforms, boarding trains, and then alighting as the trains go along. So again, the access and egress distributions are the actual observed distributions. Okay? So this gives you a sense about how variable access time is, how variable egress time is. Went through it pretty quickly, but you get the general idea. So it gives you a real visualization about the load on the train, number of people on the platform, number of people who are getting to the platform or from the platform at both ends of the trip. So this is the essence of the problem. Since then, since the simple example, we've now introduced capacity constraints. So you have denied boardings due to a capacity constraint, which is very real in London. It's very real in New York. It's very real in Hong Kong. I'm not sure whether it happens much on the light rail yet, but hopefully it will in the future. So denied boardings are a real, because of capacity constraints, are a real issue in many of the big networks around the world, and also understanding transfer demand. And when you get transfers in the network, you first of all have to really understand path choice, the transit assignment problem that Ali Reza and I were discussing earlier, which is very important. And also, you have far more itineraries in your choice set. So the maximum likelihood problem becomes more difficult in a way. So both of these are done, and these are incorporated in the doctoral dissertation of UN that's being written up now. The future work is providing advanced customer information such as expected crowding level at stations and on trains. And in order to get there for real-time information, you have to have a real-time model and application. So we have to be able to solve all this problem in real time. So we're not there yet. But this is certainly on the chart, something we think is feasible within the next few years. Okay, so that's the second application. The third and final one is measuring service reliability. And the objective here is to use these ADS, automated data sources, to develop a more customer-centric measure of service reliability to understand its effects. And we'd like to use this to improve customer communication, to give, in the journey planners and trip planners that we all are familiar with, more information on the reliability or unreliability of particular journeys. These systems are predicated on a deterministic performance. Well, we know that's not typically true. Even, I gather, on the light rail system, it's not true. But certainly on the bus network, where we have traffic interference, it's certainly not true. And so we really want to understand the reliability implications of choices we're making. And that's what this is intended to support. So the fundamental principle we're using here is reliability buffer time. So if we have a journey time probability density function like this, the travel time on the x-axis, the probability or density function on the y-axis, we're looking at the percentile between the difference between the median travel time and, say, the 95th percentile travel time, and saying, this is a reliability buffer time. If we really have to get to the airport in time to catch the train, how much additional time beyond our typical experience do we have to build in? Something we all do routinely when we're thinking about this. And this is how the journey planners should be dealing with this in the future. And we get to 95 percentile as the sort of standard thing by saying, well, perhaps we accept one-way journey per month as a bad trip without thinking this as the performance of the system. So we want to avoid things that happen more frequently than one trip out of every 20, say. It's not based on understanding customers' true preferences, but it sounds realistic. And so we're looking at measuring this reliability buffer time between the 95th and the 50th percentile. So how do we calculate the reliability buffer time? Well, we calculate it for each hour of the day over some period of time, a month or 2 months or a year, whatever it is. And the reliability buffer time measures the total variation from all portions of the trip. So if we take the MTR tap-in time to tap-out time between a particular origin-destination pair, we'll get a probability density function of that journey time, okay? And that's the simple way of thinking about reliability buffer time. What does that include? It includes access time, wait time, in-vehicle time, and egress time. Some of these are not under the control of the operator. Notably, the access time, we have some people with mobility limitations or just who prefer to walk slowly. That's an individual choice, and it's fine. It shouldn't be held against the operator of the rail service that you have that as part of the, quote, reliability buffer time. And if I, as an individual, know I always have to use an escalator or can use stairs, that will affect my understanding about how much reliability buffer time I have to build in, because I'm familiar with myself. Similarly, egress time here is an individual function. It's not a function of the service being provided, but it shows up in the reliability buffer time. In wait time and in vehicle time are clearly the responsibility of the operator. The wait time is a function of the headway distribution, and the in-vehicle time is how fast the vehicles are going and what disruptions they're faced. So that's the fundamental RBT, but includes these wrinkles, which are not under the control of the operator. And when we're dealing with MTR, MTR was very concerned about that they're being assessed for differences between individuals. So they weren't very happy about that. So in terms of journey time components, you can have reliability buffer time for the full journey time, which is what I just mentioned, platform to platform time, which includes the wait time and the on-train time, but not the access and egress time, or the run time, which is just the time on the train. You can have reliability buffer time for each one of these journey components. And passenger variance, you can look at all customers, subgroups of passengers, or individual users. And in MTR, we've done all of this, and these are some of the results. So this is a single origin destination pair for 2 months worth of data. And these bars here are showing the x-axis is time of day here, between 7 a.m. and 11 p.m. And the y-axis is reliability buffer time, between the 95th percentile and the median. So this is a high-quality, reliable service. Look at the numbers here, talking about reliability buffer times. 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. Really small reliability buffer times. We started this work in London with the London Underground. They didn't get reliability buffer times anywhere near as low as this because the system is much older, it's not as reliable, and you pay for that in terms of reliability. So each one of these bars is the individual reliability buffer time. Okay, so looking at the same individual making repeated trips at the same time of day between the same origin destination pair. And the horizontal lines are the reliability buffer time over all users is the black one, and the reliability buffer time over frequent users is the green one. And what you see here, in the morning peak, they're pretty much the same, because the only people you have in the system are frequent users who know the system very well and know how to get from point A to point B very efficiently. But even so, even here, you get big difference between the individual reliability buffer times, these individual bars, and the aggregate reliability buffer times. So there's it's much fairer to exclude the access egress differences between individuals in the reliability buffer time, which is what the individual does. If you go up here in the PM and the evening, you get lots of different people using the system. And so you get potentially very big differences between people who are very familiar with the system, this solid green line, and all users, who include people who may get lost on the system, may be unfamiliar, unsure of themselves, which is here. And so you have to be fairly sophisticated in thinking about this, particularly if you're going to use these as part of a performance regime in rewarding or punishing a contracted service deliverer. So that's the, and I won't go through the rest, but this is mainly focusing on the difference between the individual reliability buffer time and the aggregate measures. So the summary of this. First of all, complete journey origin destination estimation is now practical with ADS. London's using it as a production tool. We hope that very soon CTA and MBTA will be using it. And this is a foundation for many analyses related to the customer experience and for network planning. So we have a doctoral student now at MIT who's finishing her dissertation on looking at network design based on full journey information, which we've never had before. We never really had that. So we can use different methods. Secondly, it's realistic to assess service reliability both for individuals and for journeys. We really couldn't do this before. We knew it was important, but we couldn't measure it. Now we can. I didn't discuss this, but this is another finding that targeted online surveys are a very efficient alternative to other survey methods. So in terms of the softer data, using online survey techniques are a very efficient means for supplementing automated data collection systems. And finally, customer classification is critical in understanding the customer experience. So again, I didn't present this, but really looking at how we define fairly homogeneous groups of customers is a very important thing in really understanding behavior. And the final slide is, again, talking about future prospects. Part of what I talked about, we haven't yet completed. These are preliminary steps, and we're very heavily engaged in extending them. But we really haven't yet fully capitalized on the panel data potential here to understand the impacts of changes in service and price on behavior, to understand the process of customer attraction to the system, retention and attrition from the system. With these long time series data, we can really understand that for the first time. Informing information push customer information strategies. How do we get the customer information that he or she really needs to make the right decision on using the network, as opposed to overloading them with information, much of which is not very useful. And documenting the impacts of marketing and promotional strategies as very important. These are just simple examples of using this long-term time series panel data. And then the big elephant in the room is already in the room is the Uber, Lyft type services and how public transport responds to that. And not too far down the road is how public transport responds to autonomous vehicle technology, which we know is coming. So London and Hong Kong and Chicago are all looking at doing research to help them understand how autonomous vehicles will affect their future operations and how will affect their current investment decisions. Obviously, if you're building a new rail line, that rail line is going to be there for a long time. And so even if AV technology is 30 years away, it's going to be affecting it in the life of the investment that you're making in this capital investment. So that's it. Thank you very much, and happy to take any questions.
Thank you very much. I'm not sure how much time we have for questions, maybe one or two quick questions. Please raise your hand if you have any questions.
Hi, my name is Kristen, and you talked a lot about how real-time information will be really important, but it hasn't yet been fully implemented. So what tech will enable the automated data sources to perform in real time?
Well, I think the critical thing is, I mean, first of all, as I said, not all of these automated data sources are providing data in real time off the vehicle. Mm-hmm. So that'll be an important step. But an even more important step is having effective software to help us predict what will happen if we do a certain thing in the control center. So if we modify the operations plan in real time like this, how will people react? So it's really the integration of the demand side and the performance side in a real-time predictive context that will give us the really big impact. And I think we're just beginning to recognize that. And so we've been dealing with demand, supply, interaction, equilibrium, and dynamic processes for a long time in an offline planning sense. Now we want to deal with these in a real-time operations control and information provision sense. And I think that's really exciting for research. And I think that's where you can see the really big impacts. So we're just beginning to get into prediction, I think.
Thank you.
A couple of slides ago, you had that chart with the reliability buffer time
Yes.
versus data.
Yes.
Can you go back to that?
Sure. That one?
Yeah. So in the hours 12 to 16, you have a jump where the
Yes.
frequent users take longer.
Yes.
What do you think is causing that?
I believe this was an aberration. That there was an incident on the line. There were a large number of regular users who were affected by that, more so than the infrequent users. And so that's, I congratulate you for spotting it. It's real. It was what the data showed, but it was an anomaly. So that is not what you expect, obviously. You expect the regular users to be much more effective in terms of navigating their way around the system. They don't get lost, et cetera, et cetera. So everything else is consistent with that except for this one point, which again points to the reality and not alternative fact-based presentation of the results. Sorry, couldn't resist that.
Thank you.
Thank you very much for attendance and asking questions. We are running out of time. Let's thank Professor Wilson again, and he should be around for more questions if you have questions.